All right, here we go again. This is I'm using area models to find real roots of polynomials. This is going to very much resemble the factoring that we did here along the way. So what we're trying to do is find the real roots of the equation x cubed plus 3x squared minus 4 is equal to 0. This is what the graph looks like. We're going to use the graph to get a little bit of help. It does look pretty clearly like 1 is a place where this graph crosses, which means that x minus 1 should be a factor. We'll check that by trying to divide x minus 1 out of here. Okay, the x cubed as the leading term goes in there. So this must be an x squared to make that happen, and this would be negative x squared. But my x squareds, of course, are supposed to add up to, there's supposed to be 3x squareds, so there must have been 4 of them here, which means there must be 4 x's there and minus 4 x's there. Okay. But I'm supposed to add up to, there aren't any there, so I'm supposed to add up to 0 x's, which means there must have been 4 x's there, which must mean this was a plus 4 and that's a minus 4, which is exactly what I wanted in my constant. It was supposed to be a minus 4, and it is. So, so far, this factors to an x minus 1 and an x squared plus 4x plus 4. That's still all equal to 0, according to what we had up there. And so we can factor this part. Again, we've got it down to quadratic. So once it's quadratic, then we have better tools that we can use. We're looking for numbers that multiply together to give us 4 and add together to give us 4. That must be a 2x and a 2x. And so this would be an x and a plus 2 and a plus 2. So this becomes an x minus 1 times x plus 2 times x plus 2 equals 0. The zero product property says, well, that must mean that either x minus 1 is equal to 0, or x plus 2 is equal to 0, or x plus 2 is equal to 0. Kind of know what that one looks like. So this would say x equals 1 or x equals negative 2. And the negative 2 shows up twice. This is where our conversation about multiplicity. Okay, so a definition down here on the bottom right now says the multiplicity of root r is the number of times that x minus r is a factor. So x minus negative 2 is a factor here twice. So we would say that our answers to this are that our roots are at x equals 1, or even just that our roots are 1 and negative 2, and we would point out that this has a multiplicity of 2. Okay, we could see that one happening here as well, where it's touching the x-axis. It's obviously touching it in a different way than the graph touched at 1. In fact, at 1 it crossed, and at negative 2 it didn't. We could have written this as x plus 2 quantity squared, which would make it feel like it was a parabola all of its own, which, I mean, that is kind of looking like it's a parabola hitting right there. Maybe that starts to make sense to us of what the multiplicity does visually in a graph. All right, we got a second example here. Multiplicity of root r is the number of times that x minus r is a factor of p of x. All right, we did that. So now we're going to find the real roots of this equation. The first thing we have to do, we started this as soon as we got to quadratics, is we've got to make the thing say equals 0. So we got an x cubed. We'll subtract the 6x squared from both sides, plus 7x is equal to 0. Now I notice right off the bat that all of these have an x in them. They're the greatest common factor, and I'm going to pull that out and get an x squared minus 6x plus 7 equals 0, because now I'm all the way down to a quadratic already. I didn't have to do the area model division checking. I've got these pieces so far. And so the question is, does that thing factor? Well, I'm looking for numbers that multiply together to get me 7, and I add them to get -6. Well, boy, the only numbers I can multiply together to get 7 are either +1 and +7 or -1 and -7. They don't add up to -6. Okay, so that tells me that this thing is not going to factor. Okay. And if it's not going to factor and I'm still looking for the roots, so far I know that either x is equal to 0 or x squared minus 6x plus 7 is equal to 0, and so this is one of my roots. I definitely have that root. Okay. The other ones I'm going to have to find with a quadratic formula then. So they are at x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that is a 6 plus or minus the square root of 36 minus 28. Sounds like about an 8. All divided by 2, which I can simplify a little bit into a 6 plus or minus, that'd be a 2 root 2 over 2, and I can do some division by 2 there and get a 3 plus or minus the square root of 2. That's, with the plus or minus, that's 2 different roots. So my roots are 0, 3 plus the square root of 2, and 3 minus the square root of 2. Okay, 3 roots. It was cubic, not unexpected, but these 2 roots over here are irrational numbers. Okay? I can't write them as just a fraction of integers. These are irrational numbers, and we don't see those typically as coefficients in our polynomials. It's possible to do that, but we're not looking at those. And so that brings us to this thing called the irrational root theorem that says if the polynomial has rational coefficients, so if if all the coefficients are rational numbers, and a plus, that's too small to see, it says if a plus b times the square root of c is a root of the polynomial, of the equation p of x equals 0, then a minus b times the square root of c is also a root. Okay. So if it has one irrational root, it has 2. And those 2 are very similar. It's just one of them has the plus in the middle and one of them has the minus in the middle that we get from that quadratic formula. Okay, so it's maybe not even surprising that, that we see that along the way, but definitely shows that polynomials, when they interact with the x-axis, don't have to hit necessarily in what we would call nice places. They can hit at irrational places. But we have the tools even to find where those are.